If you go into the module, uh, under the lab handouts, I again put a lab handout for buoyancy as a doc and as a PDF. The reason why I did that is there's tables I made for you in there and equations that you can pull right out of the Word doc if you want to put them in your lab report. But the PDF is there because sometimes people's computers won't show a doc correctly. The equations just disappear. So let's look at the PDF of this. And we'll talk about this. I'm going to go to, you should be able to see my laptop, and then I'll switch back to my screen when I'm actually doing stuff. But the idea behind buoyancy is actually attributed to Archimedes. And essentially what we're trying to discover is if an, that's horrible. If an object is suspended below some water, so let's say we have a sphere. If we do a free body diagram, remember it's not moving up or down. The forces on it, there would be some force called a buoyant force. Actually, let's do this. It's attached to a string. So there's a buoyant force up, there's a tension up, and there's a weight down in the water. And this weight is mg. So we could find the buoyant force as the tension, I'm sorry, don't do that, James. The sum of the forces on here would be 0 because it's not moving, and they would equal T plus FB minus mg. And so our buoyant force would be whatever the difference in these two is. So if we could find mg, we could figure out what the buoyant force is. And how we would do that is if we hang it in the air, right? When it's hanging, the forces on it would be a tension and mg. So let's call this tension A, and this is tension B, or tension in the water. And the sum of these forces would be 0, so they would be TA minus mg. And you could find this tension, which would be mg. So what our buoyant force would be is it would be TB minus TA, because TA would just be mg, and this would be TB. Okay, and that's what we're going to do today. We're going to figure out what the buoyant force is on an object. Now, the reason why things have buoyancy is essentially if the object is less dense than the water around it, it will try to rise. So rho of the object is less than rho of the water. And vice versa, if rho of the object is greater than rho of the water. Or liquid. This is also why a balloon rises in the air, is inside the balloon, the volume of gas has less density than the air, so it rises. But we can come up with an expression for the buoyant force that is the mass of the water, okay? Now, the water is the water displaced, which means that this is the density, because density is mass over volume, or mass is density times volume. The density times the volume of the water times g. But the volume of the water is the same as the object, right? It has to be the same volume, the amount of water that was removed. So the buoyant force ends up being, and rho of water is 1,000 kilograms per meter cubed. You might have learned this as 1 gram per milliliter or 1 gram per centimeter cubed, but this is what it is, it's 1,000. G, we're gonna say is 9.8 meters per second squared. So PV is really 98,000, I'm sorry, PG is really 98,000 times V. So if we can figure out what the volume is of this object, we can figure out what the buoyant force is from that. So we could hold an object by a string in the air, get mg, and that would be our TA, and then put it underwater, and we could figure out what the tension was on B, and then we could find the buoyant force from that. Or we could measure the volume with like a ruler and multiply it by 9,800, and that will give us a buoyant force. And then the last way that we can do this is no, and I'll tell you why in a second. Is it? Did I mess that up? Yeah, I probably did. Sorry, Carolyn. let me go back. Carolyn brought up a great point. Did I mess this up? Yes, I did. FB would be, this would be backwards. I'm sorry, guys. So this would be mg minus TB, which would mean that this would actually be backwards too. And I knew that. It's actually in our lab correctly. There's something weird going on here that I'll explain when we do the lab. So basically, we could measure the volume. And if we measured it, we could multiply rho of water times G times the measured volume to get the force of buoyancy. Or we could take the tension out of the water and the tension, or the tension in the water minus the tension out of the water, and that will give us the buoyant force. And we'll talk about that. That'll make sense in a minute. And then lastly, we could actually measure the difference in mass, the mass of the water displaced. And I'll show you how to do that. And that's the one weird thing that's going to be a huge pain, unfortunately. So I'm going to show you how to do each part of that, how to find the mass, and then how to find the difference in tensions when you submerge an object, and measuring the volume, and then how to measure the water displaced. And that part is going to be a huge pain, but the rest of this is really a simple lab, okay? So essentially, we're in this lab, we're trying to find the force of buoyancy on each object. Now, what I want you to do, and I go through this, what I want you to do is I want you to find 3 objects. I would like you to use a sphere, some kind of cube, some kind of cylinder, and then something weird. And the reason why we're going to use something weird is we can find the volume and mass of the weird object using just water. We don't have to measure the weird object, and I'll talk about that in a minute. So what this all comes back to is Archimedes was an advisor to a king. The king had a crown made, and he thought the jeweler cheated him. So he wanted to know if it was real gold, but Archimedes couldn't melt it down to figure out like the volume and the mass. And he realized that he could put the crown in water, figure out how much water was displaced. From that, he could find the mass and figure out if it was gold. So we're kind of going to do that with this last object. But for now, I'm going to use a golf ball. I'm going to use an eraser as my cube, and I'm going to use a cylinder is a sheet of coins. And then I have this real weird shaped thing. Yes, and he did run through the streets naked, yelling Eureka. That's part of the story. He was in the bathtub when he found this, when he figured this out. It's a weird story about Archimedes. My 4th object, I was going to use like a toy of my son's or something just weird shaped that you can't get a volume on. This is some kind of fitting off a pipe. It appears to be brass, but if I tried to measure this volume, it would suck. Trying to measure this, I would have to make approximations and guess, and I couldn't get a real good volume. So what I want from you is some kind of ball. Doesn't have to be big, but it should be bigger than maybe a marble. The bigger, the better, not too big. Some type of cube. A dice would work, but I would really prefer something bigger than a dice. This eraser works just great. And then I have 12 pennies, and I have them in a bag just so that they'll stay together, and that's fine. So first of all, on our lab, the first thing that we need to do is we need to find the volume of each of these. So it takes you through the procedure. We're going to find, if you go down to the data table, we need to find the volumes of each of these. Now you should know that a sphere, the volume is 4/3 pi r cubed, but r is equal to half the diameter. So if you do that, if you want to get the volume of a sphere, and I gave you all of these equations, in terms of diameter, it's pi d cubed over 6. So take a ruler, make sure you're in millimeters. Just measure the diameter. I get for my golf ball, I get almost dead on 4 centimeters, so 0.04. So what I'd put here is I would put 0.04. Now, what is my uncertainty of this measurement? The resolution on this is 1 millimeter. The little mark, each little mark is 1 millimeter. The uncertainty is half that resolution. So half of a millimeter is 0.005. I could download this, but my answer would be 0.0005 meters here. And in fact, for all these x's with this ruler, it's 0.0005. For a cube, length times width times height. You guys know that, I'm assuming. Notice that my little ruler has this weird cut away. I can measure, though, the width and the length. And I can assume this is actually a rectangle as long as I measure from here to the end on the top or the bottom to the end, right? And then the height. So that's not a huge issue. Even though this thing isn't a perfect rectangle because it's slanted, I can assume that it is by measuring, right? I don't need to explain that. The cylinder, remember, that the top of these coins, if I measure this circle, the area is pi r squared. Or, in terms of d, it's pi d squared over 4. And multiply that times the height. So just take the diameter, take the height, get your volumes of those things. If you come down to the data analysis part, it gives you the volume, and then it tells you how to find the uncertainty of each of those volumes. So you need to calculate it. That's not too tough because delta L, delta W, delta H, delta D, they're all the resolution of your particular ruler. I don't know why this suddenly. Okay, and we have for the cube, we have for the cylinder. You don't have to show all of these. You only have to show for the sphere or the cube, or I think it's just the cube. But they're all there so that you can compute them for your data table. Okay, and that's all well and good. I think you guys get that. Now, your IOLab, I'm going to turn on my IOLab. As before, we're going to find the mass of each of these objects. So when you go to your IOLab and turn it on, whoever's doing your data collection, turn on the force, okay? Before you do that, calibrate it in force mode, and it tells you to do that in the lab. It tells you put it upside down, hit next, and then it says hold it. I have attached a shoelace to this thing, but hold it steady, hit next, save it. Okay, so I need to find the mass of each of these guys. And I made this so that I could hook this up. If you have a better way to do it, great. What you don't want is you don't want it to have too much extra mass from whatever you're using for your string. You can use floss. As you can see, I have a string. I tied it around the golf ball on my force meter, okay? I hit record and I just let it go for a minute. Then I hit stop. As before, if you choose a region, you need to write down the delta T and the hertz. So 1.5 seconds times 48, let's actually choose 1 second, okay? If I go 1 second, then it's not quite 1 second, but I know that I have 4,800 data points here. I need that. Let's go to here. For the weight of the ball in each air, you need the mean, which is, again, this mu is your mean. So the mean force on this was 0.637 newtons. It's negative because it's hanging out the bottom. The standard deviation is right here, 0.0065, pretty good. Sample rate is 4,800 hertz. The time interval was 1 second, I chose that. So my data points are 4,800. And again, as we've done every time with this, when we're doing the means, so the delta M is just that standard deviation, the 0.0065 divided by the square root of 4,800 times 1 over the mean value of 0.637, okay? That times 100% will give us the percentage that this thing's off. It'll be really small. Secondly, you could actually find the mass from taking this force over G. So divide 0.637 by 9.8. And you get 0.065 or 65 grams. So this thing is 65 grams or 0.065 kilograms. Leave it in kilograms. We're going to have our density of water in kilograms meter cubed. So put it in there that way. So you need to find the mass of each object. It doesn't have to be like the string. I just balance this essentially. So this one, I just kind of balanced and then got it. And one thing I should note here, when you do that, there's some small zero error here. In general, you should probably get rid of that. Subtract it from your mass. It's okay if you don't though. 0.169 divided by 9.8 is about 17 grams. So yeah, I didn't plan for it. If you want to subtract off your zero error, great. It should be 0 by the force calibration, but oh, you know what? I'm sorry. 0 your sensor. That makes more sense. I'm learning this thing as we go too. So if we go back and redo this, it seemed a little high to me. Make sure you 0 your sensor. Hit reset, hit record, hit stop. Take this off and hit continue just to make sure that it goes back to 0. Yeah, okay. All right, sorry about that. So 0.462 is my actual mass. I should probably put that in there, but so 47, that seems right. That's what I was getting last night. Okay, so we have that. Make sure you 0 your, make sure you 0 your sensor. Now, so we're going to do that for each one. You're going to write down the mean force, standard deviation, sample rate, and time interval for n. And now here's the fun part, okay? So we want the mean force or weight of each object when we put it in, when we put it in water. And so I want to show you guys something important. So you've taken the volume of each one by measurement with the ruler. You've hung them below your IOLab and gotten the force so that you could get the mass. Now the weight of each object submerged, I hope you can see this. All I have is I have a clear glass of water that has a whole bunch of air in it, but that's okay. If I go to this, reset my weight sensor, and now start recording with it out of the water. And you can see it's at whatever, 0.47. Try to keep it steady, and then sink it below the surface so the ball's just barely submerged, okay? And now what I should see is that I get, this was the weight in the air, 0.455. This is the weight once the ball submerged. This ball probably floats in the water, which is why my force is so small. My buoyancy force, though, is this force minus this force. But because they're minuses, it's actually minus this plus this, which means that you get 0.453 minus 0.06. Again, make sure that you write down on this part, this weight submerged is only the part after you put it in the water, right? It's the weight in the water, okay? So you could actually do this at one time, hold it above, get your weight in the air, get your weight in the water. Make sure, again, you write down your standard deviation, your time interval, your hertz, and your means, okay? So once you have those for the weight in there, we'll talk about water displaced in a minute, how you would find the buoyant force of each one. And I want you to find the densities, but that's just dividing mass by volume measured. So the buoyant force is subtracting those two tensions, the force out of the water and the force in the water. If you compare that to, where is my theoretical buoyant force? My theoretical buoyant force is density of water, 1,000 kilograms per meter cubed, times 9.8 meters per second squared, times the volume of the object. That is your theoretical. So for this thing, I said that it was 40 millimeters, right? Yeah. So pi times pi divided by 6 times 0.04 times 0.04 times 0.04. So I get 3.35 times 10 to the minus fifth. If I multiply that by the density of water, which is 1,000, times the acceleration of gravity, which is 9.8, I get a buoyant force of 0.328 newtons. Now, when we went back here, I had 453 and I have 0.06. So 0.453 minus 0.06 is 0.393. So my buoyant force that I get from measurement is 0.328. My buoyant force that I get from subtracting these two is 0.39. They're close, they're not great. But if you treat the theoretical as 1,000 times 9.8 times the volume you measured with the ruler, so my theoretical would be 0.328. I can do the percent error here. So I would get 0.328 minus 0.393 divided by 0.328, and I get about 20% off. That's not great. The reason why it's probably off is the string, or who knows? I don't know why it would be off. Maybe you'll get better data. I'm doing this really fast and I'm not too concerned with getting great numbers. Again, I don't care if your numbers are a little bit off. They will be. You might not get like a 5% error, and that's okay. So the last thing I need to talk about is actually the hardest part. This is the part that absolutely sucks on this lab. And that's that you need to come up with a way to figure out how much water is displaced by the object using the mass of the water, okay? So how we do this in the lab is you actually have a little cup that has a spigot that spills out water. We're obviously not going to be able to do that. So what I'm going to want to do here, if I take this off, I've got a cup, a solo cup, that I cut a hole in, okay? Cut a little hole so that I can tie it to the IOLab. I can tie it through the eye bolt of the IOLab, and then maybe I can. And essentially what I want to do is I want to use, nope, that's not enough. I want to use the IOLab as a scale. And when I do that, this stupid thing. if you'll help me. Okay. And it doesn't really matter how nicely you tie it, just make sure that you don't drop it on your computer and spill water everywhere. Okay. I would also cut off this end so that it just doesn't get in the way. Okay, so now we have essentially a cup that we can hold underneath, and keep in mind it's not the greatest, so don't spill water all over your iLab or anything else, but it'll work. So now how do we get the water? How do we figure out how much water is displaced? What I did, and you can come up with a better way, great. What I did was I put the object in a glass cup, I filled it until the water was over the object, so the object is completely submerged. Take a, this is important, take a marker, hopefully your parents don't care, put a little mark where the water level is when the object is completely submerged. This is the part that's actually going to mess up your readings. You've got to try to get every bit of water, and yeah, I just splashed some, every bit of water you can out into your cup that you're going to measure. So yeah, this is going to be kind of bad. If you go back to your force, get a reading, and then hit stop for a second. All right, put that water back in your cup, fill up to the line, fill this in, try to get all that water out, hit continue. Okay, and let it get steady, so stop it there. All right, so now what I have is the mass of this mass, this 1.181, minus this mass, 0.785, which actually they're weights, they're forces. But if I subtract the two tensions, what I get is I get the force of the water. So I can take whatever this subtraction is and divide it by G. Let's do that. So I had 1.184 minus 0.787, and I get 0.397. Divide that by 9.8, and I get 40 grams. Okay, so I get 40 grams of water. What's displaced? Do I want to do that? I want the volume. So I also would divide this by 100 or 1,000, and I'll show you that math in a second. And I get 4.05 times 10 to the 5th for the volume of water displaced. So let's actually look at that really fast, what I did. So I measured the point here. Nope. So on my graph that looked like this with some garbage, this tension here and this tension here, this tension was the water total, the total water without the object. This is the water displaced. So if I take T and call this T2 and this is T1, if I take T2 minus T1, take the absolute value, this will give me the weight of the water displaced. And what I want is I want the volume of that. But this also will give me the buoyant force on this guy. So the buoyant force that I got here was 0.397. mg is actually m of the water times g of the water displaced is actually the buoyant force. We said that we got whatever 3.392 or whatever. I don't remember what the numbers were. I'd have to go back and look. But you can compare this. You could also get the volume of that by dividing. The volume is the water displaced, so it's over the density of water times G. So it's T2 minus T1 over 1,000 times 9.8. And this will give you the same volume as the volume you measured with your ruler. You can compare it if you want. Now, what do I ask you to do in this? I don't remember. I did it last night. I ask you to, so find the volume of each object. I want you to find the volume. Oh, let me look at the table of results. It's actually easier to see there. So find the volume of each object by measurement. Find the uncertainty of each volume, and that's given, the formulas for those are given in the data analysis. Find the mass using that tension in the air. Find delta M. Find the density by taking the mass divided by the volume. And then find the difference in tension when you submerge it. Find the difference in water. So the difference in tensions when the cup, with the cup, what we just did with the water displaced. Find the theoretical by multiplying each of these volumes by rho of water times G. So multiply each of these volumes by 9,800, and that'll give you your theoretical. Again, all these uncertainties, it shows you how to calculate in the data section. Find the difference in tension, the percent difference in the tension versus the water. So the method where we submerged it versus the method where we found the water. The percent error between the theoretical and the submerging tension, and the theoretical and the water mass, okay? And finally, the last thing that you need to do for a few of these is I want to know the density here. So the density of the odd-shaped object, the only way you're going to be able to do that, and we'll go over this again, is by finding the volume of the water. So I should really dry this all out. I'm not going to. So put your object in there. Make sure you put enough water to cover it up. And again, should really dry this all out. I'm not going to though. Again, put a mark where this thing's full. Now, go through. Don't fall over. Okay. You're on. Record. Stop for a minute. Put it back in there. Pull it to the line. And this is barely. Try to get all that water back in there. Hit continue. Sorry. Hit continue. So how you orient this thing is also going to matter. I can see that I get mu. So I get 659 and about 608. So I get 0.05 is the volume of this thing. 0.05 is actually the weight of the water displaced. So the volume would be 0.05 divided by 9,800. So I get a volume of this guy. This horrible thing that would have been hard to do, because I took the difference between 0.679 and 0.609, which would actually be 0.07. And obviously, be more careful, but 0.07 divided by 9,800. So this horrible thing that I couldn't measure the volume of, I could actually find the mass of the water or the weight of the water displaced, divide off by rho times G, and it would give me the volume. And I see that I get a volume of 7 times 10 to the minus 6 meters cubed. That's helpful. That's exactly what Archimedes supposedly did to find the volume, is he just figured out the difference of the water displaced. So hopefully that makes sense to you. Obviously, our numbers are going to be kind of bad, mostly because we can't get the water out, or not being careful with the sensor. The sensor's a little hard to play with. But once you do figure out how to get the water displaced, the volume of that, or the mass of it, or the weight of it, you can find the volume by taking the weight of the water displaced, dividing by rho times g. And that'll give you the volume of this odd-shaped object. Then, because you already measured in the air by the tension, the mass of it, you can take mass over the volume, and that will give you the density, okay? What I want you to do is then look up on, for two of these in the questions, I want you to look up on the internet a table that gives you the density of metals. The reason why is, if you were to use like silver dollars for your coins, you would assume they were made of silver. And if you were to use pennies, you're going to assume these things are copper. Your density for your cylinder of coins should give you the density of copper if these are copper. I'll tell you right now, your number is probably not going to be copper. And they're mostly copper, but they're not entirely copper. And they're also in a bag with some air, and they're not a true cylinder because there's some gaps if you really look closely. They're not a perfect cylinder, so this density is going to be weirdly off, and that's okay. I assumed that this thing was brass. It turns out this is not brass. And in fact, this thing's hollow, which messes up my density. I don't care if you don't get a great number. Just take a guess at what you think it is, or what you think it should be. Perhaps you think it's copper, and copper is like 800 kilograms per meter cubed. And you get, for your coins, a density of 12,000. And copper is supposed to be 800. Then you know it's not copper, right? So just compare that. In the question section, I asked, why is it important to make sure there's no air bubbles on the object? How would they affect it if there were bubbles? This is important, the second part. The first part, not so much. If you had an object covered in air bubbles, what would happen? Well, you'd have to add that density of those, or that volume of air, to your volume. And therefore, the density would be much lower than it should be, right? So if bubbles were present on an object, your density would be much less than it should be, because it would essentially have a greater volume. Why shouldn't it touch the bottom of the cup? This is when we submerge it, when we put it in the water, it can't touch the bottom, it can't touch the sides. The reason why is, if it touched the bottom, you would have a normal force that would also affect the weight. So you'd have a buoyant force and a normal force and a tension all pulling it up versus the weight going down. And your numbers would suck. Your numbers would be off. What's heavier and equal volume of ice and water? Well, we know that ice is actually made of air and water, so it's going to have less density. But the weight is density times V times G. If V and G are the same, the heavier one has the greater density, and that's liquid water. Ice water has a lower density because it has a lot of air in it, which is weird. As I said, find the density of the coins. You have to do that anyway on your table of results. And then if they're pennies, look and see how close they are to copper. If they're silver dollars or silver quarters or whatever, see how close they are to silver, right? The last part is independent variables were things that we changed. So we chose our objects. We chose water to be our liquid. We could have chosen something else. And we chose the string, I don't know, anything that we chose. The fixed variable is something that you cannot change. You could use a different force sensor. What can't you change in this experiment? Gravity. Gravity cannot be changed. And then finally, the dependents are what we're measuring. And what we're measuring are all these tensions, all these weight forces on the tension, on the force sensor. okay? Another thing that we can't change, another fixed variable, is density of water. Although maybe we can, because we could use salt water, or we could use some liquid that didn't have the density of water. You could call a fixed variable the density of water. You could call it an independent variable that we chose water with a certain density. I really don't care which one you do. What I want to see is that you understand the difference between independent and dependent variables. And we always ask that, because when you write a scientific paper, you're going to tell the people that you're writing the paper for, or your readers, or whoever it is, you're going to tell them which variables you altered, which variables you messed with, and those variables that you're able to mess with are your independents, right? So the different masses and different volumes of our objects are our independent variables. They're the things that we twiddled with. And then we got our dependent variables, which were our different weights and our different buoyant forces out of those, okay? I think that's self-explanatory, but if you're having a hard time with those, that's what they are. So in your conclusion, remember what we're trying to do here. We're trying to prove that the buoyant force, the difference between the weight out of the air and the weight in the air, in the water. Remember, like if you go swimming, you float. So your weight is actually reduced in the water because of the buoyant force up. So we're trying to figure out if what Archimedes said is true, that the change of the weight is equal to the amount of water displaced, the mass of that water, times g. That's what we're checking. So we're comparing the change in the tension in the air submerged to the amount of force from the density of water times g times the volume of the object. Secondly, we're trying to actually find the volume that would be displaced of water, assuming that that's true. And of course, this is going to be bad because we're not going to get a direct volume of object to volume of water displaced with this method. You would have to come up with a much better method to figure out exactly how much water each object is taking up. We're losing water because it's sticking to the sides of the cup and it's doing other weird things, okay? So just remember, what we're trying to figure out is what Archimedes said true, that the buoyant force is approximately the mass of water times g, where the mass of water is the water displaced. When you talk about that, make sure that you talk about your numbers. So did you find that these forces were sufficiently close to each other? If you take the difference in tensions out of air and into water, is that basically equal to the density of water times g times the volume of the object? Is that basically equal to the mass of the water displaced times g? Okay. And then two, how accurate is your data? As always, tell me your errors. Tell me your percent error and percent difference. Third, what caused that error? There's a lot of things that cause that error, from holding the IOLab not quite correct, to maybe the string being in the water, to air bubbles, to God knows what else. There's a lot of things that could go wrong on this. So just try to think of them. And then finally, how would you improve this? If you have some great ideas of how to improve this, cool. If you don't, really just talk about eliminating error, which would be making it some way that you could actually get the difference of water. It would probably be easier to do this on a scale that actually read to milligrams, because we could then just do the water. We could cover it up and take the object out and make sure all the water got off, stuff like that. But essentially, what I want from this lab is I want you to learn what the buoyant force is, and I want you to really think about the buoyant force. And I want to demonstrate to you that basically the reason why an object floats is because its density is less. It's like all the density of the liquid crowds it out and pushes it up because they're heavier or more dense. That's why you float. In fact, you float, you have more buoyancy in salt water because salt water is more dense. There's more of a difference between your density, you're the object, and so the density of your body versus the density of the water that you displace. And therefore the water pushes you up. Same thing with hydrogen balloons or helium balloons. They're much less dense than air, so they float, okay? Why doesn't a balloon float that you blow up with your breath? Well, the reason why, if you've ever done that, you like blow up a balloon, it doesn't float, is because the density of your breath and the density of the air are the same. You need to put like hydrogen or helium in that has less density than the air in the room. Otherwise, the balloon will just fall to the floor, right? So this lab is just about understanding density. Whoever has to do the calculations, I'm sorry. The hard part is that for every one of these forces, you need to find the uncertainty. Unfortunately, our ILab doesn't give you that. But other than that, other than having to find those, these are actually not hard to do. So maybe help whoever's doing the data analysis and don't make them have to do too much work if you're doing this in groups of 3. But the rest of this is pretty easy. I mean, finding the force is mass times g, finding the buoyancy force from the different weights, finding from the tensions. These are all easy to do. The only hard part is really in the calculation section is really getting all these stupid uncertainties. And like I said, I gave you the tables, so just make sure they're filled out. One person, if you're doing this in a group of 3, one person should do the data, do the actual experiment and fill out this data table for you guys. Everything in yellow, you should figure or fill out. One person should do the calculations and the table of results. And then finally, one person should do questions and conclusion. Otherwise, are there questions that you guys have on here? And I know there'll probably be questions while you're trying to do this. I will get this done ASAP. If you can do it today, please do it today. Again, I would like you to use some like 12 coins so that you get a nice cylinder and some kind of ball and some kind of cube or eraser. And then just choose. If you have a sibling or you have something laying around in a drawer, it could even be a couple keys. You could use like 2 or 3 keys that you don't mind getting wet and that you can submerge, and then find the volume of all 3 of the keys. I don't care what you use. Just use something that you can't readily find the volume of, that you're going to want to find the volume using water displaced. That's a big, important trick that we get out of water, thankfully. Okay, so are there any questions for me? If not, I want to talk a little bit about what the lecture talked about yesterday. Before we do that, are there any questions on the quiz? If you haven't managed to look at the quiz yet, if you look at it, it should be pretty easy to do. So, hey Matt, I recorded this. You're on video. I'm going to post it after we're done. It just takes you through how to do the lab. So, okay. Last thing I want to say is, so there were really 4 things we covered yesterday in lecture. And those 4 things, I want to just review really fast for you. And they're the 4 things you need to know for the final. I did put it on the final slide, but essentially, if we used energy, we could find that PV at, let's say, let's call this 1, plus rho times V times G times H1 is equal to pressure to V2 plus rho VGH, nope, I don't need a 2 there. And we'll talk about this right now. So this is actually the first couple sections of your book talk about this. This is pressure times volume. And I don't know why I put that either. Now we're assuming that the volume can't change of an object. And so what we want to know is if we go up, move up through a column of air, this column of air has a certain volume. And we move up from, let's say, sea level to somewhere in the clouds, and then we move down. And we're moving through a column. That column has the same volume. This is 1, this is 2. So all these volumes cancel. Furthermore, we say H1 is 0, so this goes away. And we get that P1 is equal to P2 plus rho G H2. I don't know why I put a line through that. This means that P2 is equal to P1 minus rho GH2. Now, this applies for anything. This is a very general equation, but it applies for anything, okay? What that means is if we start at ground level at 0, at H is equal to 0 at the surface, the pressure is always 1 atmosphere. If we go up, we could find how the atmosphere changes, 1 atmosphere minus density of air times G times the height. So at 100 meters, the density of air is 1.2, this is 9.8, and this is 100. 1 atmosphere is 1.01 times 10 to the 5th pascals. So the pressure at 0.2 would be 1.01 times 10 to the 5th minus 1.2 times 9.8 times 100. You could find the pressure in pascals up. If you dropped, H2 would be negative. So H1 would be 0 still. H2 would be, let's say, negative 100. And what we get is P1 plus, well, it would still be minus PGH2, but H2 is negative. So this would be added pressure. As we go below the surface of the Earth, we gain pressure. As we rise up, we lose pressure. So you only have this to know. Second one that we had was what is called Pascal's lever. And if you think about a syringe, I don't know why I didn't talk about this, but a syringe, right, that shoots a little tiny, through a little tiny nozzle, right? So if this is your area 1 and this is your area 2, the force here has to equal, well, the force at 1 times the area at 1 has to equal the force at 2 times the area at 2. So if I told you that this was like 0.1 meter cubed and this was 0.0008 meters cubed, nope, not cubed, squared. And I push with a force of 10 newtons, you could tell me the force coming out here. Because F2 is F1, A1 over A2. And so here this would be 10, 0.1 over 0.0008. And so that force coming out would be 0.1 divided by 0.008, would be 125 newtons times 10, which would be 1250 newtons. The reason for that, though, and here's the whole idea behind Pascal, is that this is an incompressible, which means that its volume can't change, and it's enclosed. Okay, so anything we push here has to push with the same force out. That's a hydraulic lever, or Pascal's principle. It's super useful in some contrived examples because you always have to have an enclosed volume and one way in, one way out to use it. I mean, I guess you could have multiple ways out, but essentially it just relates force times area at 1 is equal to force times area at 2. Oh my God, I am so sorry. I am so dumb. I flipped those. I've been sick and my brain is just not working. This is actually the pressure at 1 is equal to the pressure at 2, which means, yeah, I should have realized that that was going to give me something bad. Sorry, everybody. So this would be, F2 would be A2 over A1, which would be 10 times 0.0008 over 0.1. This is 1/10, so this is 100 times 8, which would be 0.008 divided by 0.1 is 0.08 newtons, 0.08 newtons. So a big force here gives a little force here because it's a little area. We could actually flip that around and get, if we applied a little force here, right? So we could actually flip this around. Because the pressure at 1 is equal to the pressure at 2, and the pressure is FA, F over A is equal to F over A. So the force at 1 and A1 and F2 and A2, let's say we flip these. So we apply 10 newtons here, but the area is still 0.00008, and we want to know the force out. The force out is A2 over A1 times F1, which is 0.1 over 0.0008 divided by, or multiplied by 10 newtons. And what do we get? 0.1 divided by 0.0008. 125 times 10 is 1250, which is what I was trying to do. 1250 newtons. And here's the point. Big force, big area leads to little force over little area. Little force over little area leads to big force over big area, right? Because the pressures have to be the same because it's incompressible. Whatever pressure you push with on here, you push against every part of the enclosed vessel. That is important. It's actually a very important theoretical idea. So if you note that, let's say you apply some pressure to a bottle that's enclosed. Pressure 1 is here. That same pressure gets applied at every point inside, right? It doesn't, pressure is kind of a scalar and kind of a vector. It's weird, okay? It's actually a scalar. However, we visualize it as having a direction, which is not exactly true, and you need to break yourself of that habit. When you're standing in air, we say the air pressure on you is whatever, 1 atmosphere at the surface of the earth, but it's actually pushing on every part of your body with that pressure, okay? And when you're under the ocean, the water pressure under the ocean is pushing on every part of your body with that pressure. Although we tend to think of it as down on you, right? Or up on you or whatever. You've got to kind of get out of that mode of thinking of pressure that way. And then Pascal's principle says that the pressure at 1 is equal to the pressure at 2 if this is enclosed, and let's say we have a hole out, that would be P2. And we can figure that out from F1 over A1 is equal to F2 over A2. So just bear that in mind. So we have so far P1, P2 is equal to P1 minus rho GH, where rho is the fluid and H is the final height if the initial height is 0. Otherwise, what you really have is H2 minus H1. Okay. And then we have, this is Pascal's. And then we have, the final thing that we have is actually, well, no, I guess we have Archimedes that we just did, that the buoyant force is equal to the density of the fluid times the volume of the object times G. But the volume of the object is also equal to the volume of water displaced. Tomorrow we're going to have a quiz on this, and make sure you understand the example of an object where it's half out of the water. Okay, so it has a height of h, it has a length and a width. So its volume is length times width times height. But the amount that's submerged, the water displaced, the volume of the water displaced, is L times W times little h, where this is little h, okay? And the buoyancy force here is actually mg minus, I'm sorry, don't do that. The force acting on this, which is ma, is equal to the buoyant force up minus the weight down. The buoyant force is volume of water displaced, so L W little h times g, minus the weight is m of the object, which is the density of the object, times volume of the object times g, but that object, let me do this on a new slide. So the force acting is ma, which is 0, is equal to the buoyant force minus the weight. Okay, now the buoyant force is equal to the density of the fluid times the volume of the water displaced times g, and the weight is equal to the density of the object times the volume of the object times g. The volume of the water displaced is L times W times H. The volume of the object is L times W times H. Okay, since this is 0, FB is equal to weight, or P fluid, volume of water displaced times G is equal to P of object times volume of object times G. Cancel the G's, put these as LW and H, and these go away. So this is LW, H, LW, big H. Kill those, and I get P of the fluid times little h is equal to P of the object times big H. If I gave you H and H and told you it was water, then let's say H was 1 meter and little h was a half a meter, and P of the fluid was 1,000 kilograms per meter cubed. You could tell me that P of the object was P of the fluid times little h over h, or 1,000 times 1/2 over 1, or 500. So P of the object is 500 kilogram meter cubed. And you can see from here that it has to be less dense than water in order to float. If it's floating, it's less dense than water. So we know that water has a density of 1,000. It has a density of 500. Last thing I want to say, those are super easy to do. Just look up an example if that didn't make a whole lot of sense to you. It's in the lecture notes. I do that same one. The last thing is the one I want to talk about, and it's got a couple wrinkles. So let's imagine a tube, okay, that has the same area here and the same area here, but this height is 10 meters. And it's filled with water, so this is 1,000 kilogram meter cubed. And what I want to know is if the pressure down here is 1 atmosphere and the height here is 0, I want to know what the velocity is and what the pressure is here. So I want to know if I have a velocity, let's say the velocity up here was 2 meters per second. I want to know what the velocity down here is, and I want to know what the pressure up here is. All you have to do is go back to when we did energy. Okay? Just like with energy, we have an equation that looks exactly like energy. And that is that PV plus rho VGH plus rho V squared over 2. That's the energy. Get rid of the V's because the volume is going to be the same. And so I get the pressure at 1 plus the density of the fluid times G times H1 plus V1 squared over 2. This V is a velocity, this is a volume. All those V's cancel. And we set that equal to P2 plus rho of the fluid G H2 plus density V2 squared over 2. Just like in energy, we can just set those terms equal to each other and figure out which terms we have. This is the static pressure due to the water acting everywhere at this point. This is the gravitational pressure or the gravitational energy, mgh, right? The gravitational pressure, this is the dynamic or kinetic pressure, okay? Those three things are what the water has in each one. So I don't know why I called these A and oh, those were areas. Okay. So the last thing that we have is something called the continuity equation, which says for an ideal fluid, V1A1 is equal to V2A2. And this is what I confused myself earlier with the pressure. And I'm sorry that I did that. This is the continuity equation. This just says that the velocity times the area is equal at every point, okay? So for us, we know VA, the velocity at A times the area at A is equal to the velocity at B times the area at B. But if these two A's don't change, if the pipe doesn't change at all, then A and B, the areas at A and B are the same, and therefore VA and VB are the same. So if it's at 2 meters per second here, it's at 2 meters per second at the bottom. That might seem weird to you. It's because it's an ideal fluid, that the velocity only changes if the area changes. The velocity is how much water has to go past that point, okay, in the same amount of time. So really, as long as the pipe's area doesn't change, the same amount of mass can flow through. The only time it changes is if it gets smaller, right? Then it has to travel faster so that the same amount of mass can pass that point at the same time. And if it got bigger, it would slow down because the mass can travel slower as it goes by so that the same amount of mass passes that point. So that's a little bit of anti-intuition. Your intuition would say, oh, it's going to speed up because it's changing height. Well, no, it only speeds up or slows down if the area changes. Therefore, we can neglect these terms. The density of the fluid is the same, V1 and V2 are the same, they go away. Now, we know that the pressure at 2 or at B, let's call it B, so let's change these to B's and A's. A and B and B. Now, we know that the height at A is 10 and the height at B is 0. So what we get is that the pressure at A plus the density of the fluid times G times H at A is equal to the pressure at B. Or, better yet, the change in pressure, PB minus PA, is equal to positive rho G HA. Rho for water is 1,000, G is, let's say, 10, height is 10. That's 1,000 times 100. So the change times 100. The change is 100,000 or 1 atmosphere. This whole thing ends up being 100,000 pascals. And so the difference between P minus A is 1 atmosphere. Therefore, what is A? Well, A would be PGHA is equal to, I want PA, and PA is equal to PB minus rho GHA. I know that PB is 1 atmosphere. I know that this is 100,000 pascals. Well, 1 atmosphere is 1.01 times 10 to the 5th pascals. So this is equal to 0. And my pressure at A is 0. There is no pressure at the top of that tube. At the bottom of the tube, there would be 1 atmosphere of static pressure. So with all of that, what you do for these is you first note that the velocity at A times the area at A is equal to the velocity at B times the area at B. And then you use the equation energy, or it's really energy, which is why I write energy, but it's really pressure. So pressure at A is equal to pressure at B, but when I say this, I mean all 3 types of pressure. So static pressure at A plus gravitational pressure at A plus kinetic pressure at A and that little line means that its velocity is equal to pressure, static pressure at B, gravitational pressure at B, and kinetic pressure at B. Okay, so it's exactly what we did for energy, although we have different terms now. Basically, each of these terms, if they had a volume in them, would be energy. They'd be Newton meters, but we canceled out the volume. So what we're really getting is Newton meters divided by volume, which is Newton meters divided by meters cubed. So we're really getting newtons over meters squared, which is pressure, times, so pressure is newtons per area. So yeah, pressure, sorry. So we've got pressure in each of these, and therefore we're really doing energy divided by volume, but energy divided by volume is pressure. So when you do any of those problems, the only real wrinkle is that sometimes you need to use the continuity equation to substitute for VA. VA would equal B over AA times VB. And you could put that in so that you would get rid of that unknown. That's one unknown down. You can always set one of these to be 0. So one of these would go away, either HA or HB. I mean, you don't need to, but you can put one of them to be equal to 0. And then the last weird wrinkle, and this is something I talk about a lot in the lecture, is let's say you have a bucket, okay? If you have a bucket and you drill a hole in the bottom and water comes out, here, the pressure has to be atmosphere. So whatever the pressure is outside, the pressure here, if we have some water in a tank, and the pressure here also has to be atmosphere, okay? Let's say you have a pipe where the water's coming through it and it's spilling out into the air, right? The pressure here has to be atmosphere, whatever the atmosphere is. That is not always told to you. Sometimes you have to figure out what that is. Your intuition fails you really bad here, though. And the reason your intuition fails you is you want to say that coming out of this pipe, this water has some pressure. And yeah, it does. What type of pressure, though? Remember, we have static, we have gravity, and we have dynamic or kinetic. What it has coming out of the pipe is actually rho V squared over 2. But the dynamic pressure there is only P, and it's going to be atmosphere. So here, in this pipe here, it has no G because it's not changing as it passes from, let's say, point A to point B. It has no gravitational pressure, but it has static pressure at P, which is equal to 1 atmosphere. And it has dynamic pressure, which is equal to the density of the fluid times the velocity squared over 2. That's what your intuition is actually telling you that it has this pressure, but that's not the total pressure. It's weird. I know it's weird. It's hard to understand. Just make sure, and your book does a horrible job, make sure that you understand that there's 3 distinct types of pressure that can change. The gravitational pressure can change, the dynamic pressure can change, and the static pressure can change. And if you think about it that way, that there's actually 3 different terms all changing, you'll be fine. Mechanically, all you have to do is write down this term, and remember you have the continuity equation. But in fluids, your intuition will fail you a lot. Unfortunately, it's hard. So all you need to remember here is P2 is P1 minus rho G H2 minus H1. Remember that Pascal said F1 over A1 is equal to F2 over A2. Remember that buoyancy, the force of MA for an object that's floating is equal to the force of buoyancy minus the weight, which is equal to fluid times volume of water density of fluid times volume of water times G minus density of the object, volume of the object times G. Whatever the density of the water happens to be. If this is 0 because it's just sitting there in equilibrium, then this is equal to 0. If it's not, you can find this because this is actually that times, not times G. Density of the object times volume of the object times A. So you could divide through by it. I do that in that lecture notes. And then lastly, that the continuity equation times A at A, and the pressure total, which is P static plus rho G H A static at A plus rho V velocity at A squared over 2. And setting that equal to where you can set PA total to PB total. That's all you need to remember from chapter 14. If you can do those, they're great. And really the only hard thing I would say is figuring out sometimes what the static pressure is, because you just have to know that it's open to the air. The static pressure has to be atmosphere at that point. Everything else is simple, plugging stuff in, knowing what your H's are. It's not too hard. This chapter is really quite simple, I think. Tomorrow we're going to talk about pendulums, which are also really super easy. And then oscillations, which are a little hard because if you haven't done them before, it takes a little bit of getting things straight. But they're not too bad either. And as I told you guys, I'm going to go over the differential equations that govern them. That way you can see how to do them. And if you're scared of differential equations, if you think they're going to be super difficult, yeah, they're difficult. But maybe it'll get you interested in doing them, okay? I just wanted to make sure that you understand the core ideas of buoyancy here and fluid mechanics. Last thing I'm going to say about fluid mechanics, and I brought this up in the lecture, but we're assuming an ideal fluid, and pretty much everything about an ideal fluid is garbage. We assume it's incompressible, meaning the volume can't change. The volume can definitely change. You can figure out what the volume change is on water at the bottom of the ocean. Turns out it gets squeezed by pressure enough, the volume will change of water. However, at the surface of the earth, the volume doesn't really change of water. It's incompressible. We're assuming that they don't rotate. Well, we're assuming that the molecules are indistinguishable and they don't interact with each other, which water molecules obviously do. We're assuming that there's no friction, no viscosity. They don't stick together. That's definitely untrue. If you've ever seen water drops like slide down a surface, water definitely clumps up. But technically, or I guess as an approximation, the fact that water has no viscosity is pretty good. But it does kind of interact. So, and then finally that it doesn't rotate. So we don't have to worry about rotational motion. I guess there's one other thing. The viscosity also means that the velocities at any point would be all crazy. And we're assuming the velocities at every point are the same. I talk about that in the lecture. All those things are completely unphysical, and yet they give us really good answers, which is weird. Or maybe that's the problem, is that they're so simple that you would think that the underlying physics would be easy to do to give us those easy things. If you've done any thermo and seen how like everything comes back to the ideal gas law, and you're just like, well, why don't we just use ideal gases? Well, a non-ideal gas is really hard to understand and hard to figure out the physics of it, what's happening in it. Fluids are impossible. There's just, you guys are all young. I'm old enough to remember when we didn't even have enough space. Like basically your laptop could almost run fluid dynamic simulations that will give you pretty good data. Back when I was a kid, you needed a supercomputer to do it. And now we can almost get there. But there's a math prize of $1 million if you can understand and solve some of the theoretical parts of fluids. Just know that. The reason why I'm telling you all this is basically our physical model in the book, all this stuff that we're doing, it only applies if they're ideal fluids, and nothing in real life is an ideal fluid. So if you go to grad school for bio or physics or engineering and you have to do fluid mechanics, it's a lot more complicated. I wrote my thesis on fluid mechanics through nanopores. It's a huge, huge, painful equations to do. So just know that everything we're doing is making wildly invalid physical assumptions, yet they work, which is pretty cool. Anyway, tomorrow I'm going to post a lecture on chapter 15. That's the last of our material. It's pendulums, which are super easy, and oscillations, which may or may not be easy for you. Hopefully, by the time you do a few of them, you'll understand them and they'll be easy, but they might not be easy. They might take a little bit of work. And then we're done. On Thursday, I'm going to do a pendulum lab for you. We're going to do a pendulum lab. I'm going to need you to find something that you can mount. So think about this if you're doing this. Something that you can mount a string to that you could hang like a mast from and let it swing back and forth. I'll show you what we're going to do in that video. It's pretty cool. We're basically going to use the light sensor to get the exact time of the pendulum. And then we're going to learn that a pendulum, the period, the time it takes to go back and forth, doesn't depend on the mass, and it doesn't depend on the angle that you start at. It only depends on the length, which is really, really interesting. And hopefully you all can understand why that would only depend on the length. Now, we know enough about torque, which a pendulum works due to torque, due to gravity, to understand why a pendulum only depends on the length. And so we'll go through that and how to use pendulums to get meaningful information. Turns out you can use them to find gravity, the constant of gravity, anywhere. Secondly, you could use them to find like how fast a Tyrannosaurus Rex walked, and that's pretty cool. We can figure out, I was watching Jurassic Park 2 with my son, and they said something like a T-Rex runs at 32 miles an hour. We're going to figure out how fast it walked using pendulums. Super easy to do, but cool. And then we're going to talk about oscillations. And oscillations, what it really boils down to is you have a wave equation for the position, and you need to figure out what the amplitude of that is, what its angular velocity is, and what its phase are. And once you have those, you have the whole system solved. Everything else is just plugging in numbers into equations. So hopefully that'll be fast and easy, and you guys will enjoy it, and then we'll be done. The last thing that I want to say is the last thing I wanted to say was, so tomorrow, pendulums and oscillations, chapter 15. Thursday, pendulum lab. I'm going to post probably tomorrow after lecture, I'm going to post the exams, the practice exams for the final. The final will have pendulums, oscillations, some kind of fluid, and some kind of gravity question. So next week, we're going to have, Monday will be a review of gravity and angular momentum, gravity, and probably maybe pendulums and fluids. I don't know. We're going to divide it up though, so that it's about equal material on Monday and on Wednesday. However, here's the thing. Keep in mind, I'm going to post a homework after I post a lecture for pendulums and oscillations tomorrow. We are done a week from Thursday, which means anything that you have that you need to get to me, you need to get to me by next Thursday. I'm going to get the labs, the impulse and the the vector lab and the other lab graded today if I can. But anything you need to get to me and anything you've gotten to me that I haven't graded yet, I'll grade. I know I have some things of yours, James, but get your homework in if you're getting homework to me. Just make sure that we're running out of time, and I'm not going to accept anything after basically Thursday night. If it doesn't come to me on Thursday night, it's done. So we're going to quickly run out of time. Before you know it, we're going to be done and moving on. So you'll have homework assigned. You already have Buoyancy. Chapter 14 was assigned yesterday. Chapter 15 will be assigned tomorrow. You'll have till Thursday midnight to get it done. I'm going to post practice finals without solutions. On Sunday, I will post the solutions to homework. I guess it's homework 9 from yesterday and homework 10 from tomorrow. You'll have solutions to those on Sunday. You'll have solutions to the practice finals on Sunday, as always, except now we'll have till Thursday to study for it, okay? So hopefully that's enough time. The other thing I'm going to say is there will be some comprehensive stuff on the final, meaning there might be a projectile motion. We'll talk about that. You'll see that. There might be some kind of block sliding on an incline. You'll see that in the practice finals. But so I owe you by tomorrow. I owe you your 3 labs graded. I owe you a new homework, and I owe you the practice finals being posted by tomorrow. So I'll get all that stuff done for you. The lecture on pendulums and oscillations, I might not record a new one. I might record or use the one from last semester again. I just need to watch it and see if I screw anything up in it. And again, I'm sorry earlier when I did the Pascal's thing that I screwed that up. I've had a fever and I've been super tired. I don't think it's coronavirus. I think I just have the flu. But I actually had a fever when they checked me yesterday at my son's dentist. So hopefully I don't completely crash. I'm going to try and get everything done for you. If for some reason I totally get sick, I will make sure that those lectures get posted for you tomorrow. So anyway, before we go, any questions? Otherwise, I'm going to get out of here and grade some labs later this afternoon. Any questions? If not, I'll talk to you guys soon. See ya. Bye, son.